Our next topic in the class is going to be net ionic equations. Net ionic equations have to do with showing the important parts of a reaction and what's really going on behind the scenes. A lot of reactions involve parts that in the written equation aren't really all that pertinent to what's really happening in terms of what you see. So net ionic equations are used to show the specific ions and atoms that are really involved in the reaction that we see from the outside. There are parts that usually aren't involved, and we can kind of remove those in terms of really understanding the true guts of what's going on, and net ionic equations help us to do that. Net ionic equations are simpler than a complete or full equation because they leave out the reactants and products that aren't really affected. There are parts of most reactions, but not all reactions, but parts of many, that really aren't changing in any way, and so they're just kind of watching the reaction happen around them. If we can remove those, we call them spectators. If we can remove those, we can get it down to a little simpler reaction a lot of times. That'll help us to really see what's going on. We're going to start on net ionic equations looking at double replacement reactions. They're probably the simplest way to start looking at them right up front, and then we'll move on to some single replacement reactions and synthesis and decomposition as well. Now, you don't need to write the italics down here because this is already something that you should have in your notes from, I believe it's video 5.2. But just remember that in double replacement reactions, cations and anions switch partners more or less, and when they do, a new product can be formed. When it shows up, it's often a precipitate that shows up as a solid that can't dissolve, so that's an insoluble compound. And so we're looking for that insoluble compound as kind of the thing that we see with our eyes. As you do this for double replacement reactions, you're going to need to use a solubility table. Now, if you're in my class and you're watching this video, you should be able to find your solubility chart in the back of your lab manual on page 167. If you're watching this video and you're actually not in my class, you may have to dig around for a solubility chart, or you could use a list of solubility rules as well. This is the one that looks like, and that's in our book. Again, it's table 3 on page 167, and it's a table that'll give you the solubility for a couple hundred compounds existing with cations that you see here down the left-hand side and anions that you see here across the top. Depending on what you're looking for, you can find most any common compound that you might be asked to consider on this solubility table. So take a minute, find that chart or one like it, and have that near at hand for the work you're going to do. On a solubility table, as I mentioned, you'll combine various cations and anions together into ionic compounds, many of which are soluble in water. And it's important to remember as you look at that chart that it is just for water as the solvent. We need a whole different chart if we're dissolving a solute into ethanol or nitrobenzene or cyclohexane or some other goofy solvent, most of which we'll never work with in an inorganic chemistry class at the high school level. So at this point we're going to focus on water-based solutions and the solubility of things in water. You'll find that there are compounds on that chart that are going to show up listed as a capital S for soluble, meaning that they can be dissolved in water, and they'll make various ions, cations and anions, that are loosed from each other, separated, and are free to combine with other cations and anions potentially into those precipitates that we're looking for. And so as we work with equations, we'll be looking for the ones that are soluble and insoluble. The soluble ones will be designated with an AQ. As we've been talking about in class, there are states of matter that we use abbreviations for in our equations, and one such state is a solution. We use an AQ to show an aqueous solution. And so the other compounds will be the ones that we're concerned with anyway, will be insoluble. The ones that cannot be dissolved are those precipitates. So if we try to dissolve sand in water, it's not soluble. Well, there are lots of other compounds out there, ionic compounds, which sand isn't, that can't dissolve in water either. And when you look those up on the solubility chart, you'll find that they are listed as an I for insoluble, cannot dissolve in water. Generally speaking, that means they won't dissolve in water at room temperature, and in most of those cases, they won't dissolve in water even if you heated it up. To show those in equations, we're going to use the symbol for a solid, specifically here an ionic solid or crystalline solid. So we're going to use Cr as our state of matter. Now you might find that a solid symbol, just the S for a solid, works just as well. And again, if you're watching this video and you're not in my class, your teacher might want you to use a solid just as an S. That's fine too. But generally, it's just most important that we can designate the difference between one that dissolves in an aqueous solution and one that doesn't. You might find on your chart that there are some slightly soluble compounds listed, SS's. There may also be some that are decomposing in water, or some that are just left as a dash. More or less, those are compounds that really can't be made at all and won't exist long enough to even be tested. So the first thing you'll need to be able to do, and that's what this video is all about, is to find the solubility for each reactant and product in a double replacement reaction. I wouldn't say you need to write this little paragraph down here. It's just kind of guiding you toward the first task at hand, and that is to be able to look up any compound on that chart or a solubility chart like it, or use a list of solubility rules maybe, and to be able to determine whether or not something's going to dissolve. If it's soluble, we'll split it into its ions. So what I'd like to do with you is have you look at an example of sodium chloride. Take a look at sodium chloride on your solubility chart and see if you can find where it's listing its solubility as either soluble or not. If you look at the solubility table for sodium chloride, the idea will be go down the left-hand side under the cations to sodium, so it's very near the bottom, and then across to chloride, which is the fifth column over, and you should find that sodium and chloride, where they meet down here, is listed as an S. And so that means that that particular compound is, in fact, soluble. So we can split sodium chloride into cations and anions. So we'll take a look at sodium chloride, and we'll split it up into exactly that. Sodium ion with a +1 charge, and chloride ion with a -1 charge. And now, important to notice here, we're putting charges on these, so these are ions. And the AQ is really important to show as well, because those ions are dissolved into water. Ions really don't exist in any state except dissolved into a solution, unless we're working with plasmas, which we're not. And so an aqueous solution in this case involves sodium ions dissolved into water plus chloride ions dissolved into water. Why I emphasize that so much is that the difference here is that this is not a decomposition reaction. We've been looking at and studying and practicing a lot with decomposition reactions. If we decompose sodium chloride, it would turn into sodium metal and chlorine gas. And those are very different things. This is ions that we're dissolving it into, and so this looks like a decomposition reaction when in fact it's a dissolving equation and not really a reaction per se in the same way that we've been looking at them. So it's important to note there that, for example, here chlorine does not show up as chlorine diatomic, but as chloride in the ion form. So when you're working with solubility, you don't want to think about elements as being diatomic because they're not truly elements. These aren't truly elements on the right-hand side of the equation. They're ion forms or ion versions of the compounds, or rather the elements that we're talking about. So this is sodium ion, not sodium the element. And this is chloride ions, not chlorine the element. There's a really fine line mentally there, but once you start to understand that there's a pretty big difference, it'll come a lot clearer. Last thing you want to do is sort of balance this out. Now, many of these are very straightforward to balance. In fact, dare say all of them are quite easy to balance. The basic idea being that one sodium chloride unit breaks into one sodium ion and one chloride ion. Okay, pretty straightforward. Let's look at another example. This is aluminum bromide. Aluminum bromide, if we look that one up on the solubility chart to decide whether it's going to dissolve or not, because that's the first question, we can go over here to aluminum bromide. Here's aluminum, very top row. And there's bromide very near the corner here. And so here's an S. So sure shooting, aluminum bromide is soluble too. So we're going to take aluminum bromide and we can split it up. We're going to get aluminum ions and we're going to get bromide ions. Now in this particular compound, because aluminum has a +3 and a -1 for bromine's charge or bromide's charge, we get AlBr3. And so when we split them up, we not only want to show those charges, +3 and -1, but we want to show this then in the balanced equation that from 1 unit of aluminum bromide, you'll get 1 aluminum cation and 3 bromide anions. So we want to kind of balance that equation out. From 1 piece breaks into then 4 separate ions. 1 cation aluminum and 3 bromide anions. 1 piece becomes 4. It's important to be able to think that way a little bit here, and as we get into a topic later in the year, you'll find out that the number of ions formed in a solution like this is really important too. Finally, let's look at calcium nitrate as a soluble example. I just want to show you how we handle one with parentheses. I think you probably would be able to get this, but I want to show you one anyway. So here's calcium nitrate. Again, if we look back at the solubility chart, calcium, and come across all the way to nitrate, you'll find that it's soluble too. Not only that, pretty much every nitrate compound is soluble. So nitrate in general is a very soluble ion. As we come back then to write that up, calcium nitrate would split into a calcium ion with a +2 charge and 2 nitrate ions with a -1 charge each. Important to notice here that we do separate the 2 nitrates from each other, so there's no more parenthesis here and no more 2 behind them. But we do not separate the nitrogens and the oxygens from each other. The nitrate itself does not come apart in water. The idea being that water really can't separate the covalent bonds, in fact in this case multiple bonds, that hold nitrate together. Nitrogens bonded to oxygens are not bonds that water can pull apart. However, calcium and nitrate ions are attracted by electrostatic forces that water can pull apart, and does pull apart in this case. So calcium nitrate breaks into one calcium and two nitrates, three separate pieces from the one original piece. Finally, one example of one that's not soluble. So here we have cadmium hydroxide. And again, if we look at the solubility chart for cadmium hydroxide, we'll find cadmium, about the sixth one or seventh one down here. We come across to hydroxide and you'll find there's a big I right there, all right, in the middle of your chart. And so that's our first example of one that's not soluble. So cadmium hydroxide will not dissolve, and so you can't split it. It won't dissolve in water, so we can't dissolve it on paper. And so cadmium hydroxide remains as cadmium hydroxide and does not come apart. Basically, the left side of this line equation looks exactly like the right side, because the stuff wouldn't come apart, wouldn't dissolve. If I put some cadmium hydroxide into water and stirred, it would just kind of swirl around, and then the powder would settle back to the bottom of the container and wouldn't really dissolve at all. So we show it here as a CR. Anything that's insoluble remains intact, stays together as one compound, and does not separate into ions apart from each other. So we don't see that here. Now you're going to have a list of these with about 16 or so on it to try. I'd like you to try maybe just the first 4 or 5 and see how you do. And then next time we're together in class, we'll work on a few more of those and take some questions, go through any that you might have trouble with. This is again just the first part of net ionic equations. We'll move on further to what we do with these after we've split the ions up, and we can work with the double replacement reaction in greater detail then as our next video. So we'll talk to you then, and thanks for watching.